sorry. I had a first slide. Angles in the coordinate plane. Now we're kind of switching into new stuff you haven't seen before. We've had our 2 days of review. Congratulations. We're done with that now. Now new material from this point on, pretty much. Hooray. When we work with angles in the coordinate plane, and I put a little sketch pad here to demonstrate this, what we're going to do is we're always going to deal with what's called standard position in trigonometry. The positive x-axis is going to be what we call our initial ray, always. So going out the positive x-axis can be our initial ray. My terminal ray is always going to be somewhere else at an angle. Oops. This can be hard to do. There we go. And you'll notice that as I move this around, what happens to the angle measure? It increases, doesn't it? We've dealt with angles in geometry plenty, so we can get the idea of angle measure. But this terminal ray here can be depending on its position. Now, Sketchpad isn't going to go past 180, but for trig, we are. So, that's interesting. There we go. So now it's counting backwards, but in trig, what we're going to do is we're actually going to say, all right, it's not going to be 122. This is going to be over 180 degrees. So now we can start having angles greater than 180 degrees. We can have angles greater than 360 degrees by rotating around more than once. Maybe this is actually the angle that started here, went all the way around, and then ended up there. But standard position angles always have the initial ray heading out the positive x-axis. And this kind of makes sense with the way, remember yesterday we talked about quadrant names? And you've probably always wondered, why do we start with quadrant 1 in the upper left and go around counterclockwise? Why do we do it that way? Because of standard position. Okay, this is quadrant 1. And as we increase our angle measure, which direction are we going? This way. Making that quadrant 2. This is the second quadrant we encounter in standard position. This is quadrant 3, and this is quadrant 4. So it makes sense as we rotate our angle in standard position, now suddenly the quadrant names make total sense. Of course that's the way they're going to go, because the first quadrant we go into, then the second, and the third, then the fourth. Just a little reminder, when we're dealing with quadrants and angles, if a point is actually on an axis, it's not in a quadrant. If we had a point right down here on our terminal ray, we wouldn't say that's in quadrant 3 or quadrant 4. We would say that is on the negative y-axis. So points on the axis are not considered to be in a quadrant. They're on the axis. Points can be either in a quadrant or on the axis, not both. All right. So when we draw an angle in the coordinate plane, the vertex is at the origin. The initial side is on the positive x-axis. The terminal side could be anywhere else. We measure the angle rotating counterclockwise from the initial to the terminal side, counting up, as long as we're rotating counterclockwise. This is called an angle in standard position. So maybe this right here would be about 120 degrees. Let's just kind of guess. That will be what a 120 degree angle looks like in standard position. And yeah, we're making it nice by putting the center at the origin. The vertex of that angle is right at the origin. That makes it really easy to work with. If the vertex of the angle wasn't at the origin, what might we want to do? Let's say the vertex of the angle is actually up here. You want to know what we do in more advanced mathematics when the vertex isn't in a place we like it? We shift our coordinate system so it is at the origin. We just do a shift of the coordinate system. So, yeah, pretty much working in standard position is what we're going to do almost all the time. And if we're not in standard position, that's more for a calculus thing. We shift the axes. So it is in standard position to make life easier. Just a quick note about standard position. We almost always in trig use the positive x-axis as the initial ray and rotate counterclockwise. Physics, navigation, and other applications have a different idea about standard position. For them, the positive y-axis is the initial, and you rotate clockwise instead of counterclockwise. Think of a compass. Due north is 0 degrees, and then 90 degrees is east, 180 is south, so you rotate the other direction. That is confusing. And we're actually going to have problems in here that require us to use navigation coordinates instead of standard position coordinates. So we have to kind of eventually adapt ourselves to using both methods. For now, we're going to stick pretty much with the trig system. And don't blame me for this. It's not my fault they use two different measuring systems. It's just kind of the way it is in between math and science. And so we have to adapt a little bit to them and be prepared for something different. But for now, we're just going to go ahead and use our trig standard position for what we're doing. We measure the angle in units called degrees. You're used to that. We are going to get a different measurement system very, very, very soon called radians. But for now, for today, we'll work with degrees because you're used to that. But realize there are many different ways of measuring angles. And some people get really confused by that, but just think of length or volume or any other thing we measure. I mean, we have different measurement systems we can use. You can measure length in inches or in centimeters, right? You can measure volume in quarts or liters. We're used to the idea of working with different measurement systems, just not with angles. But the time is going to come very, very soon where we have to. Unlike in plane geometry, we can have any angle measure. I've already kind of talked about this a little bit. And we're going to talk about the idea of rotations. First off, how much would a full rotation, if we did just one full rotation all the way around, right back onto itself, how many degrees would that be? 360. Okay? So what would a 3/4 rotation be? 270, yes. How about a half rotation? You all said 180. How about 2/3 of a rotation? Luckily, 360 is a number that divides easily by a lot of pretty simple fractions. Yeah. 120, well, careful. 1/3 would be 120, so 2/3 would be 240. Good. 1/6 rotation, 60. 2/5 rotation, 144. Got the calculator out? That's what I would do. But let's think outside the box. We can have more than just fractional rotations. We can have larger rotations. How about 2 3/4 rotations? Yeah. 990? How about a negative 7/8 rotation? What do you mean by negative rotation? That means going the opposite direction, rotating clockwise instead of counterclockwise. What would that be? If I rotated clockwise 7/8 of a rotation, how many degrees would that be? Well, 7/8 of 360 is come on. Get out the calculator if you need it. What would it be? 315, but since it's rotating clockwise, it would be negative 315 degrees. Yes, we can have negative angle measure, which is something unheard of when you took geometry. We never had negative angle measure. We said that was nonsense in geometry. This isn't geometry. This is trig. We're bigger boys and girls now. We can handle more advanced concepts. Remember back when we used to say you can't take the square root of a negative number? Yeah, now we know, yeah, you just need the I. As long as you got I, we're good. We can do whatever we want. We can have complex numbers. We can have negative angles. The world's a bigger place than you thought it was. All right, so we can have that. Now, like I said, counterclockwise, positive angle, clockwise is negative angle, but we do have a little bit of a tricky situation here, in that if I rotate 1/4 clockwise, like you see indicated here, that's negative 90 degrees. But if I rotate 3/4 counterclockwise, I have 270 degrees. And they're exactly the same, aren't they? Which one is it? How do I know? If I see this picture, if someone draws this angle in standard position, says what's the measure of this angle, how do I know, is that negative 90 or is that 270? Or maybe it's neither. Maybe it's a full rotation plus that. So I'd have to add another 360 to 270 or 630 degrees. Or maybe it's 2 rotations around, so it'd be 990 degrees. Which one is it? It's a little ambiguous, isn't it? Because I can get multiple answers for the same angle, multiple different representations, multiple different measurements. When that happens, we refer to these angles as coterminal angles. Remember we called this the terminal side? The initial side and the terminal side, coterminal angles. Coterminal angles have exactly the same picture, and they're just different measurements, and those measurements always vary by exactly 360 degrees. I mean, if I take 270 minus 360, I get negative 90, right? 270 plus 360 is 630. And I could find an infinite number of angles, if I want to, that have that same picture and different numbers associated with them, simply by adding or subtracting 360 each time. That's going to be one of your homework problems today. They're going to give you an angle and say, name an angle that is coterminal with this angle. That'll be something you'll be asked to do. And all you have to do to find a coterminal is to add 360 degrees or subtract 360 degrees. It's pretty simple. The primary angle is usually considered the one between 0 and 360. That's usually our primary measurement. Although sometimes we might choose between negative 90 and 270 for some things in the future. So, just so you know. A few little things. You're going to see Greek letters in this book. We're going to use them as variables instead of X, Y, A, and B. We'll still use regular, Roman letters as variables, but sometimes we'll use Greek as well. There's a chart of Greek letters in your book. If you're going to join a fraternity or a sorority when you go to college, you might want to memorize those because, that's how they're identified. But common ones that we'll be using here are theta, alpha, beta, gamma, and phi or phi, depending on how you want to pronounce it. The letters of the Greek alphabet. These are all the lowercase letters. There are uppercase as well. Just like our letters, they have uppercase, lowercase, and Greek alphabet. Sometimes they look very similar, just like our letters. Sometimes they look very different. But again, expanding your world a little bit. We're not going to just work with English. We're going to have a little bit of Greek there. So angles are often measured in terms of a variable theta. And what they're going to do is they're going to tell you, okay, here's the initial position of our angle, and then I want you to do this many rotations on it. What would the measure be under those circumstances? So here it says theta is 38 degrees, and you do 2 rotations counterclockwise. Well, counterclockwise, since we're going counterclockwise, we will be adding or subtracting the 360s. Adding. Counterclockwise is positive. So we'll add 2 counterclockwise rotation says 38 plus 2 360s, or 720, so that's 758 degrees, would be the angle that is coterminal with 38, or the result of starting with this angle and doing this rotation. Yes?
Theta is not always 38?
No, theta is just a variable, like x is a variable in the algebra equation, or, yeah. We just use theta to represent an unknown angle. It's just that when we start running out of, we only have 26 English letters, and when some of them are reserved, like, you know, E and I, so we don't use those as variables, and eventually we just want to have something else to work with. We want to have a bigger pot to choose from. So you'll have problems that look like this. They give you an initial angle, they give you a rotation. It might not be a whole number of rotations. It might be 1.5 rotations counterclockwise. Then you'd add 540 degrees, wouldn't you? It was 1.5. The only thing you have to decide is if you're adding or subtracting the number. Counterclockwise, we're going to add it. Clockwise, we'll subtract it. Pretty simple. So two angles that are coterminal with 235. Any two angles? Again, to find coterminal angles, we add or subtract what value? 360. So if we added 360, that would be 595. I could add another 360, or let's subtract the 360. Oh my gosh, we have to do some subtraction of 3-digit numbers. Can we handle it? Or do we have to whip out the calculator? But it would be negative. And we could obviously keep going on by adding, subtracting 360, find more if we want. Very simple. A critical skill that you are going to need in here, fractions, and working with fractions. We are going to spend a lot of time working with fractions and counting with fractions here. Essentially, 12ths. That's going to be the base we're going to use most often as part of this class. And every year people get mixed up because they can't do that fraction thing in their head. They get really messed up by the idea of the fractions. But let's just look at our adding by 12ths. This is not in your homework tonight, but this is kind of getting you prepared for stuff that we're going to do very soon. If I go by 12ths, 0 12ths is obviously 0. We got 1 12th, 2 12ths, which reduces to 1/6. 3 12ths is a quarter. 4 12ths is a third. 5 12ths, which does not reduce. 6 12ths is a half. 7 12ths does not reduce. 8 12ths is 2/3. 9 12ths is 3/4. 10 12ths is 5/6. 11 12ths does not reduce, and of course 12 12ths is 1. The idea of counting by 12ths is going to be important to us, and understanding that. Now, in reality, what we're going to be working with, we don't do the ones that don't reduce for the most part, which makes it less obvious, because the numbers we deal with are actually the 1/6, 1/4, 1/3, 1/2, 2/3, 3/4, 5/6, and 1. But realize they have that common denominator of 12, and really all we're doing is going by 12ths. So a lot of times it's easier to think back to them in terms of 12ths instead of in terms of the normal denominator of like 1/6. Think of it as 2/12ths. Now, where is that going to come in? Let's look at it just a little bit differently. Let's multiply each one of those values by x, some variable. If I take x times 1/12, I get x over 12. That's fine. If I take x times 2/12, I get x over 6. Because I reduce the 2/12 to 1/6, and 1 times x is just x. Or I could think of that as 1/6 x, either way. 3/12 is a quarter, so quarter x, or x over 4. 4/12 would be x over 3, and you're getting the idea pretty quickly, how we do these fractions. Basically, the idea here is I want to get your brain primed for the idea of looking at and working with the idea of x over 4 plus x over 3 as a very normal thing. When you see that, you don't have to freak out and go, oh my gosh, what do I do? How do I understand x over 4 and x over 3 together? They're not the same denominator. I'm kind of preloading this because I want you to say immediately when you see that, go back to, oh, x over 4, 1/4, that's 3/12. That's 3x over 12 plus 4x over 12. Oh. Or 7/12 x. See, we're still within our denominator of 12s, aren't we? So combining these terms, we always just go back to the 12s. But people get really messed up with the idea of x over 4 and x over 3 if they can't get back to that idea of 12s. And so, like I say, I'm just kind of preloading this idea for you. I want you to be ready for this when it comes up, which is going to be soon. So I just want you thinking about that. Not part of your homework at all. Your homework tonight is very much based on this sort of thing. Finding coterminal angles, doing rotations, stuff like that. Pretty straightforward. And to put that on the board for you, as we are running out of time, it's PLC day. Pre-calc homework. There we go. I realize it's a little small sometimes, but I'll just read it off. It's page 15, 2 through 12 even. The 16 through 28, only multiples of 4, so 16, 20, 24, and 28. Only 4 problems there. 32 through 46 even, then 51 and 52. You'll notice we do a lot of the story application type story problems. I always want you thinking, how does this work with some real life situations? Always want you working on that. Okay? Yeah, we got about a minute.